Okay. All right, let's get started. How is everybody? I'm glad. Today we're going to talk about probability. Probability is going to be the basis for how we model and compute under uncertainty in artificial intelligence. So if we take a step back, and think about what we've done so far in this class, we've thought a lot. Mostly, there have been some exceptions, right? In expect max and MDPs, there were probabilities. In reinforcement learning, there was some learning. But mostly, what we've done in this class is we've thought about symbolic ways things can chain together and how to do reasoning using computation along those kinds of models. What we're going to start to talk about today is something we've mostly ignored to date, which is uncertainty. There's a lot of things that happen in the real world where either you can't or you don't want to have a fully detailed model that explains every last thing to the point where what's left is deterministic. Often your model is incomplete or incompletable, and that shows up as uncertainty about what's going to happen. Things can be out of your control, or they can simply be things that you can't compute. So in this middle part of the course, we're going to talk about probabilistic reasoning, which is our main formal mechanism for talking about and reasoning about uncertainty. And then in the last part of the course, we're going to talk about machine learning, which is, you can think about that as how we learn the parameters that go into the probabilistic models or models in general that we'll be talking about now. So probabilistic reasoning is used for a lot of things. If you remember back the brief history of AI, in the first decades of AI, we tried to write down lots of rules and chain them together, and that gave rise to interesting kinds of computations, particularly for things like games that actually do work according to those kinds of logical rules. But then that didn't scale because of uncertainty, and we needed methods to be able to cope with that uncertainty. That's what we're going to talk about now with probabilistic reasoning. And a lot of the recent advances in, say, the past decade in artificial intelligence have to do not just with reasoning about uncertainty, but about learning about how the world works through data, through experience, and that will be the last part of the course. So today, in some sense, is going to be a preview of all the things we're going to be seeing and working with, and all of the techniques and ideas for the next several lectures. So on one hand, we're going to see all kinds of stuff today. On the other hand, pieces of it are going to seem familiar because you've all seen some kinds of probability or statistics in other courses, and we're going to lay all that out today. So in some ways, today is going to be the most sweeping lecture. And in other ways, it's going to be the most nitty-gritty kind of computational low-level lecture there is in this class. And so please keep in mind that the stuff we're going to use today, we're going to see today, we're going to use over and over again. So the goal for today is to really know all the stuff we talk about today cold, so that when you see these things, you just intuitively get what they are. And so this is something that it's worth making sure that by next lecture, anything that's new today is you've really sort of gotten a chance to wrestle with it and internalize it. You're going to need this stuff a lot for the next few weeks. We're going to talk about random variables, which is our key method of modeling uncertain outcomes. We're going to talk about joint and marginal distributions. We're going to talk about how to compute conditional distributions, which are the quantities we actually care about, uncertain values given evidence. And we're going to talk about a lot of the mechanics that form the basis of the graphical model infrastructure that we'll use over the next few lectures, both for models that don't have time and models that do, for which we'll have hidden Markov models later. All right, so here we go. We'll begin with Ghostbusters. So I'm going to show you a demo. This is like CS188 Ghostbusters. The probability is sound. The spectral theory is totally made up. Okay, let's see. We're going to play Ghostbusters as a class. And this is going to illustrate both what's involved in accumulating and managing evidence and uncertainty, and also how frustrating it is to not have something to help us compute posterior probabilities of variables we care about given evidence. So the way this game works is on this board somewhere there is a ghost. Okay, you'll see later versions of this in your projects for which there can be more ghosts. But for now, there's one ghost on this board, and it's somewhere. Our job is to figure out where it is. We get one shot. We click bust, and we're either right or wrong, and we get an appropriate utility. We can also take sensing actions. So we can drop a little probe, and it'll tell us about the density of spectral emanations or something like that, and we'll get a color back. What does the color mean? The color is going to be red. That means we're right on top of a ghost here, all the way down to green, meaning ghosts seem to be distant. But there's going to be noise. Okay, so before I do anything, I want to show you the noise model. The noise here is given by a bunch of probabilities you can see on the bottom of color given distance. So for example, if the ghost is 3 away, the probability that you get a red is 0.5. So everything is uncertain. And sometimes you're right on top of the ghost, and you get a green. And sometimes it's clear across the board, and you get a red. And that's super frustrating. So let's play. All right. I will sense here. All right. Ghost is sort of nearby. I'll sense here. You can see my score is dropping because it costs 1 point every time I sense. I'm going to sense here. Okay, well, maybe we're getting close. Let's dig around here. All right. Okay. Is it there? Is it there? Well, who knows, right? Maybe. All right. Apparently, you know what? I bet uncertainty's off. Nope. There we go. All right. So we get a bunch of sensor readings here, and at some point, okay, there's this trade-off, right? At what point should I stop paying for sensing moves and just bust? That's a value of information computation. It's a super cool concept, and we're not going to do it today. Today we're just going to stop, okay? So I've decided to stop. I'm going to bust. What should I do? Well, where do you think I should bust? CS188 guided search here. Should I bust here? No. How about here? No, I'm just trolling now. How about here? Yep. Okay, let's do it. Ready? We got him. Okay, good. All right. So that is Ghostbusters, and we got 228 points because we got him, but we sensed a whole bunch of times. All right. So let's look at that one more time. I just can't get enough. Okay. All right, let's look at this one more time. Right now, if I asked you, hey, where's that ghost? What would you say? Well, first of all, you don't know. You can't know. You don't have enough evidence to know. So you would say something like, I don't know where that ghost is. It's sort of somewhere. Each location might be equally likely if that's how the game is set up. Okay? So your prior distribution here says uniform probability. But then once I start getting some sensings, some sensor readings here, at this point, where do you think the ghost is? It's, maybe it's more likely to be kind of left or kind of top. That sort of heat map in your mind, how likely each square is given the evidence you have, that's the posterior distribution. That's what we'd like to be able to compute on the basis of the evidence. We don't have the tools to do it yet. We'll get a lot of those tools today and even more of them in the next couple of classes so that we can say precisely exactly what probability is in each square. And then if I get enough of them, maybe, okay, I still have no idea. All right, so I'm going to bust. I'm going to go for it. Miss. Close. Okay. There we go. You don't always win at Ghostbusters. All right. So that's the basic idea. That's going to be a running example through a lot of this, is that there's some quantity you don't know. In this case, that quantity is the position of the ghost. That'll be represented by a random variable in your model. There are other quantities, like the results from the sensor probes, which you do know. In addition, you know how the things that you know are connected up probabilistically to the things you're curious about. And then you do some computation in order to compute the probabilities you want. That's what probabilistic inference is about, and we're going to lay the groundwork for that now. So here's a general situation. You're going to have a model. What is a model here? A model is going to be a collection of variables. These are going to be random variables because sometimes you know their value, but sometimes you don't. When you know the value of a random variable, that's evidence, right? It's not uncertain anymore. So those are going to be the observed variables. And you're going to know certain things about the state of your world. Here that's sensor readings, but if we were doing medical diagnosis, the random variables that you observe as evidence might be symptoms or lab tests or something like that. They're going to be unobserved variables. And these are all the things you don't know the value of. For example, in this case, where the ghost is. But there are other unobserved variables, like what reading you would get at a different location. In a medical diagnosis case, there might be unobserved variables like other tests you didn't perform but still could. So there's the evidence. There's the query variables that you actually really care about right now. And then there are going to be other variables that may also be unobserved, and you need to figure out how to work with them as you do your probabilistic reasoning. And then finally, you've got this model. And what the model is here, that's a word we use a lot in AI. And what the model means here is it's a description about how the known variables relate to the unknown ones. Today, that's going to take the form of a giant joint distribution, which is a big lookup table of probabilities. And as we go further into this unit, we'll get more and more sophisticated ways of specifying compact models that let us do very complicated and powerful queries. Probabilistic reasoning is going to be a framework for managing our beliefs and knowledge. That means taking all those relationships you know about between the variables, taking the evidence you have, and then doing computations to produce quantities that you can use to make decisions. For example, the decision of where is the ghost most likely to be, or what is the expected utility of doing a sensing action at a certain location. Those are going to be things that we need to know probabilities conditioned on our evidence in order to do well-founded decisions. All right. Any questions before we start? Because we're about to do a tour of probability and probabilistic concepts that's going to serve you well for the rest of this course. Yep.
Will we also consider uncertainty on sensors and stuff like that?
Are we also going to consider uncertainty over sensors and things like that? So in the formulation here, that uncertainty will show up in the random variables that represent those sensors. So if I had a deterministic ghost sensor, the probability of green, given the ghost is 6 squares away, would be maybe 1. It would be deterministic. Probability 1 means deterministic. A noisy sensor might say, well, at that distance, you're 90% likely to get a green, but 3% likely to get an orange. That's noise in the sensor. Now, a lot of sensors are real-valued kinds of things. Like I take a laser measurement or something, and I get a distance back, and it might be slightly off. So the format of the noise in a sensor is going to vary based on what kind of distribution, and that's something we'll talk a little bit more as we go. Okay. Yes? Will this week's material be on the exam? I think so. We'll see. We'll tell you clearly where it's stopping. The exam doesn't exist yet. Okay. All right. Starting with probability and probabilistic concepts. First concept, random variables. These are actually a lot like something from CSPs, which were variables. A random variable is an aspect of the world which you care enough about to put in your model. You give it a name, like, for example, the variable r might represent whether or not it's raining. T, in this running example, we're going to have that might be whether it's hot or cold. D might be how long it takes to drive to work. L might be where's the ghost. And so we're going to put variables in our model. And these are things either that we can observe, or that we might want to infer about, or other variables that help us write down how the world works in a probabilistic way. We write these down with capital letters. They're just like variables in a CSP in the sense that they have domains. So, for example, R, is it raining, might have the domain true or false. All right. You guys have been seeing true or false forever, but there's an important shorthand we have in CS188, which is that when possible, when names aren't ambiguous, we have a shorthand where we write something like R equals true instead of writing R equals true, which takes a lot of space and I can't spell. Instead of writing R equals true, we're just going to write plus R. Okay, so plus means true, minus means false, and the lowercase r means the variable we're talking about here is the capital version of that letter, so capital R. So you can think of this as true and false with typing, right? So that we can write things more compactly and more clearly. So we might have a variable like T, hot or cold, that takes on values hot and cold. Now it's binary, but not Boolean. We might have variables that are continuous valued. So something like how long will it take to drive to work could be real valued. That could be a time. You could have things that are discrete valued but not binary, maybe even structured in their values. So where is the ghost might be some enumeration of positions on the board, 0, 1, 0, 2, and so on, x, y positions. Okay, so we can give these variables big domains, small domains, continuous, discrete. In this class, we will almost always be talking about discrete domain variables. All these same concepts we talk about work in the continuous case, but the mechanics are more complicated. So all your sums turn into integrals, and you got to think a lot more about some kind of corner cases where things get degenerate. Okay, so it's just like CSPs. We've got variables that talk about the important properties in the model, and they have values in a domain. What's new is we now have probabilities that are associated with the values. So, for example, for temperature here, we might be hot or cold. We might have a probability distribution over that random variable. And here, the probability distribution assigns a number to each outcome, and those numbers have certain properties, like they're positive, they sum to 1. Okay, so here, 50-50. That's a uniform probability over the outcomes hot and cold. Here's weather, right? This is not, it's still discrete, but it's not binary anymore. So this one says sun has probability 0.6, rain has probability 0.1, fog has probability 0.3, and there's an outcome meteor that has probability 0. Okay. So this gives you a sense of what a probability distribution over 4 values looks like. There's actually this is a well-formed probability distribution, but it's actually a big no-no to put zeros in your probability distribution. So I probably wouldn't do this if I was building a real robot weather crisis model or something. I would probably replace that with something like, some appropriate small number, because once you put a 0 in your probabilities, all kinds of weird stuff can happen. And what you generally want to say is, well, that's very unlikely, but should evidence come into my observations that is consistent with that outcome and not with the others, I eventually want to conclude it anyway. So you only put 0 in for things that can never, under any kind of evidence, happen. For the slides, it's nice to have zeros, but that's a big no-no in real models. All right. So unobserved random variables have distributions. So they look like this. A distribution is a table of these values. So when we talk about a distribution, that's a table. When I write a distribution, I write something like P of capital W. When I see a capital, that means it's like an array. I have a value for every value in the domain of that random variable. When I write something like P of W equals rain, that's not an array anymore. That's now a single scalar value. So a probability is a single number. So in this case, P of W is this whole table. P of W equals rain is this one entry in that table, and therefore is associated with a scalar rather than a table or vector or matrix or whatever of numbers. All right. The properties, in order to be a legal licensed probability distribution, all the entries have to be positive, and they have to sum to 1. Okay, 0 is allowed, but usually a bad idea in practice, and we'll talk about why later. All right, oops. Let's erase this first. We have the shorthand notation. Don't let it confuse you, which is that we often drop the variable equals when it's unambiguous. So if T is the only thing that can be hot, we'll sometimes write something like P of hot, or P of cold if T is the only thing that can be cold. But if there are multiple variables that could be hot or cold or true or false, we have to write the variable names as well. That's why we have that other notation before where we might write P of plus R to indicate variable R has the value true. This only works if domain entries are unique, which we'll try to do for examples. All right. Joint distributions. Joint distributions are the heart of probabilistic models. They have all the information about the domain, about all the variables, about all the interactions between the variables, but they're very big, so we avoid actually computing them in their full glory whenever we can. They're sort of like search spaces. They're too big to actually write down, but if you use them in the right way, you can sort of do anything you need to in a probabilistic model. So a joint distribution over a set of random variables, it could be 1, it could be 2, or it could be n, specifies a real number, the probability, for every assignment. And an assignment is just like it was in CSPs. It is an outcome for each value assigned to each variable. So we might write this as the long way, variable x1 has value lowercase x1, variable x2 has value lowercase x2, but much more often we use this shorthand. So this probability over these n variables is one number. If I put capital letters there, it's a big n-dimensional array that has a number for each outcome. Okay? So here is the joint probability over the variable t for temperature, which is binary here in this model, and w for weather, which is also binary. And so their joint probability has the outcomes hot sun, hot rain, cold sun, cold rain. This should feel like a truth table. It's the same thing. Except now there's a probability assigned for each of those. From this, I can now answer any question you want about temperature and weather in this model. I could answer questions like, how often is it sunny? Well, it's hot and sunny 0.4 of the time, and it's cold and sunny 0.2 of the time, so how often is it sunny? 0.6. I can go to this table and compute any derived quantity I want. This joint distribution has to obey some rules, but they're pretty lax, right? The rules are just positive numbers and sum to 1. The actual numbers and which numbers are bigger than others specify what's likely, what correlations exist between the variables, what the probabilistic dependencies are, and will become much more important when we start breaking these tables up into graphical models. Problem with joint distributions. On one hand, they're your key to answering any question about a domain you can ask. Probability of this given that and so on is their size. So let's say you have n variables, like up here, and each one has a domain of size d. How big will this table be? Any guesses? ND. We have ND as a guess. Anything else? I heard D to the N. Anything else? All right, well, let's think about it. What does this table do? So I've got each of these variables, one variable x1, x2, x3, x4, and for every assignment to that sequence, I get a number. So as that sequence gets one more element, let's say it gets another true-false element at the end, how many more numbers do I need? Twice as many, because I have all the values where it's true and I have all the values where it's false. So this is going to be exponential. You have one number for each variable's assignment, and that means that it's going to be exponential in the number of variables. That's usually your sign that something is going to get very expensive and very bad. Okay, so for any real model that has, real graphical models can easily have thousands of variables, you can never write this joint distribution in the same way that you can never write out the whole search space. But that didn't matter to us back in search because we only needed sort of the part of the search space we found during our search process. We started at the top and we sort of were selective about creating and instantiating the search. It's going to work a little differently here, but as we get more tools over the next several lectures, we're going to be very careful to not build the whole joint distribution. We'll only build the corners we need in a sort of on-the-fly, in-demand way. But today, we're going to do the gory, expensive brute force thing, okay, so that we can make sure we understand all the concepts there. So, joint distributions get very, very big very quickly. Okay. Probabilistic models. What is a probabilistic model? Well, it's just a joint distribution. That's it. A probabilistic model is a joint distribution over some random variables. Okay, they're going to have random variables which have their domains. The assignments here are called outcomes. And the joint distributions say not whether they're possible, like in a CSP, but whether they're likely. So this probabilistic model over temperature or weather says that hot and sun together is reasonably common, but hot and rain together isn't very common. Okay? These probabilistic models are normalized. You're going to see this word a lot. Normalized means when you add everything up, you get 1. Okay? It's one of the properties you need to be a legal distribution. And ideally, only certain variables directly interact. The thing that's going to be the foundation for our ability to do efficient inference over very big models is that the interactions are sort of not every variable connects to every other variable. For today, that won't matter, but that'll be very important starting next lecture. This should look a lot like a CSP. So what's the difference between something like a distribution over T and W here with hot and sun and cold and rain versus a CSP over those same variables? They're actually very, very similar. The difference is a CSP can be thought of as specifying a giant truth table, right? For each assignment to all of the variables, it's either true, meaning it passes the CSP's constraints, or it's false, meaning it's illegal according to the constraints. Now, we never wrote CSPs out like this, right? You would take those 300 countries and their colors, and you would write this giant exponential size assignment to all of the colors to the map, and then you would write at the end T or F. We didn't do that. We broke it into little pieces that says these two can't be the same and these two can't be the same. And we're going to do the same thing with probabilistic models. We're going to say the probability of this variable depends on this variable in the following way. But again, not today. A couple more basic definitions, and then we're going to start to derive interesting computations from these things. Events. An event is a set of outcomes. Remember, an outcome is a complete assignment to all the variables. Okay, so if I say the probability of some event, and there are multiple assignments that match that event, I have to add them up. In general, when you collapse together probabilities, you talk about the sum of their probabilities because you're talking about the probability of anything in that bundle happening. So from the joint probability, we can calculate the probability of any event, many of which we don't care about, but there's a certain class of events that we're going to care about all the time that we'll get into in a second here. So let's look at the probability that it's hot and sunny. Well, that's this row. So computing that event, it's a single outcome. I can look it up in the table. But the probability that it's hot is not directly in this table. It has to be derived from this table. So I can take this table, and I can say, well, that row is a case where it's hot, but so is this row. And how do I get the total probability of hot under this model? I add them up. In this case, I would get 0.5. Okay, this particular event, where one of the columns mattered and the others didn't, this is a marginal. We'll talk about these in a second. But this is a common kind of event we think about, is a case where we care about some variables' values, but not others. But we can do all kinds of stuff. Like we could do, instead of hot and sunny, that's a single outcome. Hot, that is a collection of outcomes there that ignore one of the variables. Or we could talk about hot or sunny. That's the top 3 rows of this table. And if I add up all their probabilities, I get 0.7. Okay, so as my events get bigger, their probability is going to grow. Okay? Any questions on that? Almost all the time in this class, the events you care about are partial assignments. So something like T equals hot, or W equals sun, or T is hot and W equals rain, and not these kind of OR events, kind of a bunch of arbitrary things ORed together. We tend to not actually use those. All right, let's do a quiz. We're not going to do like a stop and discuss quiz. We're just going to do a really quick eyeball the thing and give yourself a couple seconds. So, what is the probability according to this probabilistic model, which is a joint distribution over x and y? What's the probability of x and y both being true, or plus x plus y? 0.2. We looked it up in the table. All right, what's the probability of plus x? 0.5. You get that by adding up these two rows. Another way I can talk about this is I can say those two rows are consistent with plus x. We're going to use this term consistent with probabilities a lot. You'll notice we talked about consistency in search. That had to do with heuristics and a certain kind of triangle inequality. We talked about consistency in CSPs, and that meant something entirely differently. It's going to mean something entirely different here. When we talk about consistent with probabilities, we're talking about matching variable values that are known. So the rows here in red are the ones that are consistent with plus x, meaning they match that partial assignment. All right, so I could also talk about the event minus y or plus x. What would that be? That's also this. That's 0.6. Okay, great. Marginal distributions. A marginal distribution, this is one of the harder names to remember. They're called marginal distributions because they used to publish certain kinds of distributions that are that have two variables as a two-dimensional table. And they would sum up for you the rows and the columns. And when you have a two-dimensional table and you sum up all of the rows, those sums would go at the end in the margins. Okay, that's where that derives from. So a marginal distribution is a subtable. So if I take a probability, if I take a joint distribution, it says for every combination of multiple variables what their probability is. A marginal distribution is a smaller table in which some of the variables have been eliminated. When you eliminate variables, rows collapse together. Like if I eliminate W here, hot sun and hot rain collide, right? They're both P of T equals hot. When things collide, you add them together. That process is called marginalization or summing out. So for P of T, I can take P of T, I can derive it from P of T comma S by summing out all values of S for the given value of T I care about. So if I want probability of T equals hot, I add up probability of hot comma sun and hot comma rain. That is this equation. So connect this equation with that idea that you've already done intuitively. It's summing out the dimension S, which here is the variable W. Of course, there's also another marginal of this table. This joint distribution also has a marginal probability over W, which gives the probability of sun and rain with the temperature marginalized out. Okay? So from the joint distribution, you can derive the marginals. Do you think it works the other way? So it'll be a puzzle for next time. It's certainly the case that if I give you the thing on the left, you can derive the thing on the right. But it's actually tricky to go the other direction. There's a problem with it. We'll talk about that next lecture. Okay? All right. Let's do a quiz on this. Marginal distributions. Here is a marginal distribution over x and y, which both take on the plus and minus value. That's their joint distribution. So for their joint values, we have the probabilities. I'm going to compute a marginal now. So let's compute the marginal over P of x. Well, it's got entries for every value of x, but ignoring the distinction in y. So for P of plus x, I look at the consistent rows in the joint distribution, which here are the top two. I add them together. This is called summing out for that reason. And what do I get? I get 0.5. Okay, that was this row and this row are consistent with plus x. I add them together. I get plus 5. Now I could do minus x. I could do it the same way algorithmically. I could take all of the rows in the joint which are consistent, meaning matching, plus x. That's the bottom two. And I could add them together. And what would I get? 0.5. Or I could do it the sneaky way, and I could just take 1 minus what I've already gotten, because I know they add to 1. Okay. All right. That's P of y. Stare at it for a second. Think about it in your head. What's P of plus y? 0.6, and P of minus y? 0.4. Okay, great. That is creating a marginal distribution from a joint distribution. Now, in this case, the joint distribution had two variables. It was a two-dimensional object, and I created one-dimensional objects. The joint distribution might have 100 variables, and I create a marginal distribution over just one of them. I have to do a whole lot of summing things. Or I could create a marginal distribution over 99 of those 100 things, and the table's still big, but less big. So any subtable, whether it's the smallest or nearly the entire thing, or even technically the whole thing, can be called a marginal distribution. Okay, questions on that? Now we have the core concept in probabilistic reasoning, which is the computation of conditional probabilities. Okay, in and of themselves, conditional probabilities are pretty simple to state. The conditional probability of some event A given some other event B. So in general, you've got some universe of outcomes. You've got the region here you can see on this Venn diagram. What do we know? We know that B has happened. That means we're in this circle here. And what we'd like to know is how likely is it that A also happens given that B happened? So graphically, that's how likely is it that we're in this purple part in the middle given that we're in the red. Okay. Mathematically, how do we compute that? The definition of a conditional probability is the ratio of the joint probability, A and B, divided by the probability of B. And you can think of this as what proportion of the B outcomes are also A outcomes. Okay, that's the definition of conditional probability. So that's one of the rules we're going to have when we start having to compute things, is this definition that we can compute conditional probabilities, A given B, from joint and marginal probabilities, A comma B and just B. Okay? Let's do some. So here's T and W again. We can compute things like, what is the probability of sunny given that is cold? Well, we remember the definition first. We can do this the long way first. So first it will be the probability of sunny and cold divided by the total probability of the conditioning event, which is C, which is cold. And the numerator, P of S comma C, is sitting in this table, probability of cold and sun. So that's 0.2. And the denominator is not sitting in this table, but I can derive it. What's the total probability of cold here? It's 0.5, but notice it's also 0.2 plus 0.3. Okay, what does that mean? Notice the numerator is part of the denominator. The denominator consists of cold and sun, but also cold and rain. And this is going to be something that's important for some of the algorithms that come up. I'll show you more examples of it as we go. Okay, so there's the computation there. Okay, quick quiz on conditional probabilities. Let's do probability of plus x given plus y. And for this one, the first thing we'll do is we'll remember the definition. That's the probability of plus x and plus y divided by the total probability of plus y. So what's the numerator? Plus x and plus y is 0.2. Plus x, total probability of plus y is 0.6. And that's going to be 1/3. All right. I'll let you do the next one yourselves. Probability of minus x given plus y. All right, who's got an answer in their head? Okay, I'm going to do it. I'm going to do the whole thing. This is probability of minus x and plus y divided by the total probability of plus y. Minus x plus y is this row here, so that's 0.4. The total probability of plus y is that row along with that row. Those are the two rows which are consistent with plus y. And so together they're 0.6. That means 2/3, and you could have also gotten that sneakily by noticing that this is everything other than the 1/3 we just computed. All right, I'll let you guys do the last one yourselves. Okay, so this is the point where you start getting like, yes, I understood all the pieces, but actually I'm having to access them all in all kinds of combinations really fast. It is really good to practice this stuff because it does have to get mechanical. All right, in addition to conditional probabilities, which so far have been numbers, there are conditional distributions. Like any other distribution, they are a vector of numbers that describe a probability of various outcomes that sum to 1, except these outcomes are conditioned on an event. Okay, so here's a joint distribution. This is that same distribution over the hot and cold variable t and the sun rain variable w. And we can compute various things. Like, for example, we can compute the probability distribution over w given the evidence t equals hot. Where did we get this? Well, first of all, what does this mean? Because there's a capital letter here, this will be a distribution over w. Anytime you see a capital letter, you think at a data structure level, this thing is an array in that dimension. So when I see P of capital W, this is an array over all of the values W can take. So there's going to be an entry for sun and an entry for rain. Each one of them is going to be P of sun given hot and P of rain given hot. Okay? Let's compute one of them. Let's compute P of sun given hot. That's equal to P of sun and hot divided by the total probability of hot. And that is P of sun and hot is 0.4. Total probability of hot, 0.5. And you can see that 8 is sitting there in that slot. You can compute the other one as 0.2. But there are other conditional distributions. There's also a distribution over P of W given T equals cold. And there's at least one other thing you could talk about here, which is the marginal probability of P of W. Okay, so let's compute that. P of W, this is a distribution. It has a value. Remember, it's a vector for W. It has a value for sun and has a value for rain. And what's the total probability of sun here? 0.6, total probability of rain, 0.4. And so I can look at this and I can say, all right, before I had any evidence, if you had said, hey, what's the probability of sun today? I would have said 0.6. But if you tell me it's hot, that belief, that posterior probability condition on the evidence goes up to 0.8. That sort of makes intuitive sense. So maybe this joint model isn't totally crazy. But if I tell you it's cold, now the probability of sun drops from 0.6 to 0.4. So what I'm starting to get is I'm starting to get qualitative changes in variables of interest like, hey, what's the weather? That change as a function of the evidence I get. And where that changing probability is a function of the joint model, which specifies sort of everything, and the evidence I get. And this is a lot of what we do with probabilistic models, is we build a joint model, and then we ask various questions. Hey, I have this evidence and this evidence. Tell me about this variable. Oh, I got more evidence. How should my belief change? And that updating of beliefs in a well-founded way is a big part of what we're doing here. Any questions about conditional distributions? A conditional distribution is a distribution. So as a data structure, it looks like P of W, but semantically, it is conditioned on evidence. So it's not the same as the marginal. Okay. Let me stop and ask questions before you discover the normalization trick, which will serve you well. Okay, so one thing you do a lot in probabilistic reasoning is you compute conditional probabilities. And in particular, you usually want the whole distribution. Like, you don't really care how likely is the ghost to be right here. Oh, 0.004. I don't know what to do with that. But if you give me the whole distribution, I could do something like take the maximum and bust there. Or I could do a calculation, a utility calculation. Usually you want a conditional distribution over your query variable, but given the specific settings of the evidence that you have. So a lot of your queries look like this. You have some joint distribution that has the variables you care about and also the other variables, including your evidence. And then you want something. Like, I want to know the probability of the various weather outcomes given that I've observed that the temperature is cold. All right, well, how do we compute that? Well, okay, so we could actually compute it. So first of all, what's the thing going to look like? The thing's going to look like it's a distribution over W, so there's going to be sun and then some number, and then rain and then some number. So as a data structure, it's going to be a distribution over W. How am I going to get each entry? Well, we did it before. You kind of compute, you use the definition of conditional probability, and you say, all right, well, first I have to compute the top one, probability of sun given cold. What's that? I go back to my definition. Oh, that's the probability of sun and cold in proportion to the total probability of cold. And you say, well, the numerator was easy. It's sitting in the table. And for the denominator, I went and I added some things up. Okay? So where's this in the table? Sun and cold. It's right there. Okay. So what's that total probability of cold? Okay, don't go into symbol shock here. Look at what these entries actually are. This is sun and cold in the numerator, and the denominator is that and the other thing. Okay, rain and cold. So then I go to the other entry in this table, and I say, okay, and there are the numbers. I go to the entry in the other entry of the table, and I say, okay, what's the probability entry for rain given cold? Well, I pull out my definition of conditional probability, and I say that's the probability of rain and cold in proportion to the total probability of cold. This is sort of like what I did up above. And when I expand it out, I see now it is a different entry of the joint distribution. So now this is rain and cold. Okay, rain and cold. That's this one. Divided by the same thing, right? So that denominator is the same. It's still the total probability of cold. And importantly, that denominator is just the sum of the two numerators. So that's a key thing. Whenever we do these conditional probability computations, we're always dividing by the total probability corresponding to the sum of all the different numerators. And that means we don't actually have to compute it. So the hard part about this computation is the denominators, and you don't have to compute them. So the way the normalization trick looks is like this. So ignore the other computation for now. Here's the algorithm for computing a conditional probability. You say, all right, I have a joint probability distribution. Great. Someone has asked me for a probability. Like somebody has asked me, hey, I would like you to compute for me the probability distribution over the variable w given t equals c. So what you do, rather than trying to think about each cell of that independently, we're going to think about this like a database or a table operation. And this intuition will really help you when we get into building and doing inference over Bayes nets and graphical models. So you're going to take your joint distribution. You're going to think of it as a big multi-dimensional array or a database table. And what we're going to do is we're going to do various operations. The first operation we do is a select. We select the rows that are consistent with, meaning they match our evidence. So what's our evidence? Our evidence is that the temperature is cold. So I eject those rows. They are not consistent with my evidence. So I'm left with only the rows that match my evidence. Now they still vary on W, but that's good. Okay, but they all match my evidence on T. So that's select. You select the joint probabilities matching your evidence. And now I have a smaller table. What did this original table add up to? It adds up to 1. It is a well-formed, normalized probability distribution. When I selected some of the rows, what does it add up to now? Not 1, right? Because I just took some of the rows out, and the other stuff that just got ejected was part of the summing up to 1. Okay, so I look at this and I say, all right, well, it sort of looks like what I'm looking for. It's sort of like a distribution over W for my evidence, except it doesn't add up to 1 anymore. So what you do, you can write this thing as P. You can write a lowercase c, because it's no longer an array over that dimension, comma W. But then I normalize. I make this selection sum to 1. So the step is select the probabilities matching your evidence and then normalize. So when I normalize, what does that mean? How do I make it sum to 1? Right? I don't go in and just like change the numbers around sort of arbitrarily. I keep their proportions, but I divide them by their sum. So in this case, I would divide them by their sum, which is 0.5, which is that same quantity that kept showing up in the denominators. Okay, so mechanically, I've got a probability distribution popping out, because it sums to 1, and there's a value for sun and a value for rain. How do I know it's the conditional probability over W given T equals C? Well, selecting got me the right numerators, and normalizing is going to get me the right denominators, because if I think of these values, if I add them up, cold and sun plus cold and rain, well, that's just the total probability of cold. And so the total there is going to be P of C, which is the denominator for the conditional probability I want. So, to compute a conditional probability, select and normalize. Any questions? Think about this like operations on a big table. You select rows, you normalize what's left. The algorithms for Bayes nets are going to work like that. All right. We just talked about that. Okay. Now we will compute the conditional probability over x. That means plus x and also minus x. The conditional probability over x given the evidence y equals minus y. So what do? First I select some rows. What rows do I cross out? Okay, I heard the first one. That one's toast. Doesn't match my evidence, minus y. Third one doesn't match my evidence either. That one's toast. So we select. Oh, I guess I got to write them out. You select and you get plus x minus y and 0.3. And you get minus x minus y 0.1. Hey, look, everything that's left matches my evidence. Of course it does. I ejected everything else. All right, so I've got the rows that match my evidence, and now I normalize. What do they add up to now? At present, they add up to 0.4, which actually turns out to be the probability of minus y. Okay, so I'm going to normalize, and I get for plus x and for minus x. For plus x, I get 0.75, and for minus x, I get 0.25. And then if I draw some lines and write P of W over that, it's a distribution over W. But it's not the marginal distribution over W. It's the distribution over, X is the distribution over X. Okay, it's not the marginal distribution over X, it's the distribution over X given the evidence minus Y. There is also a distribution over X. It's a different distribution. And I'd find it in a different way. I do that one by collapsing all the rows that match on the X coordinate. It would be a different computation. Let's do it. Let's do that one. Let's compute P of X. That is also going to be a distribution over X, so it's going to be a number for plus X and a number for minus X. All right? Except this time, I still extract it from the same starting position. Pretend nothing's crossed out with red. Okay? So start thinking in your head how you're going to do this. Well, for plus x, I have to add together, or marginalize here, I have to add together all the values that match plus x. That's 0.2 plus 0.3, that's 0.5, and that means the other one's going to be 0.52. So this is a distribution over x. This is also a distribution over x. The one on the left is the marginal distribution over x, meaning no evidence. The one on the right is the conditional distribution over x given the evidence minus y. There's also a conditional distribution over x given plus y. You can find that one for yourself if you'd like practice. Any questions? All right, we're getting pretty close. Okay, we already talked about how to normalize. You might wonder where this name comes from. If you look up in the dictionary, it says restore to a normal condition. What is the happy normal condition we are restoring when we normalize a row of numbers? It's their sum to oneness, right? They sum to 1. We selected some rows. They don't sum to 1 anymore. They're freaking out, right? We normalize them. They're all happy again. They sum to 1. They're a good probability distribution again. Okay, so we talked about the procedure there. Okay, let's take a 2-minute break, and then we'll talk about probabilistic inference in general, where we'll talk about what happens when you have much bigger things that have other variables in there that you don't want and also don't know. And then that's going to give us basically the overview of what we're going to then redo in the next few lectures in an efficient way. So 2-minute break, and then we'll continue with generalized probabilistic inference. All right, let's get started. We only have a couple more pieces, and then aside from this minor issue of exponential costs in time, space, and sample complexity for learning later, you will have all the tools for probabilistic inference. That minor thing is actually a major thing, and it'll drive a lot of what we do for the next few lectures. But as a basic idea, we've been talking about probabilistic inference. Probabilistic inference is when you compute a probability you want, like, hey, where's the ghost given my evidence? Or what's the probability of, this heart condition given these evidence values? Or how likely is this to be spam given the words in it? Or whatever that is. You're computing a desired probability that you don't know until you compute it from other probabilities that you do know. So, for example, you have the joint probability, but you'd like a conditional. So you do some work and you add these things and you normalize and so on. Or you have one conditional and you want to compute the other. That'll be through Bayes' rule, and we'll talk about that in a minute here. But in general, probabilistic inference is going from a set of known probabilities to the desired probability. The desired probabilities are usually conditional probabilities. So I might want to know something like, in my model of driving to work for a lecture, in that model, how likely is it that I will be on time given that there are no reported accidents? And maybe the answer, I do some computations on my joint distribution and I compute 0.9. These will represent the agent's beliefs given the evidence. So a rational agent in this sense will have beliefs which correspond to the conditional probabilities over the variables of interest given their evidence. Now, as you get new evidence, your beliefs can change. So the probability that I'm on time given no accidents might be 90%. But if I'm also driving in at 5 a.m., it's even more likely I'll be on time. But if it's also raining, it's maybe less likely again. And this fact that observing new evidence variables causes your beliefs to update. Okay, that's an important part of kind of rational intelligence. All right. The general case for computing a quantity from a joint distribution is an algorithm called inference by enumeration. It is an exponentially slow thing operating on an exponentially large table. Okay, so this is in general not going to be tractable. But the algorithms that we are going to use that are often going to be more tractable, you'll be able to see that they perform the same computation, but in some kind of interleaved or efficiently structured way. In the same way that enumerating outcomes for a CSP until you find one that works does actually tell you what the CSP does, but it's not particularly efficient. So we're going to do the inefficient thing to build intuition, and then we'll start doing more efficient computations next time. So the general case is you have a whole bunch of variables, x1 through xn, and you have a joint probability distribution over them. So it's big. It's exponential in the number of variables n. It's very big. Okay? From this very large table, you're going to have some evidence, like maybe variables e1 through ek, that might be x1, 3, and 7, have values. I know that it's raining. I know that the lights are on. Whatever it is that you know. Those are your evidence variables. You then have a query variable. Sometimes variables, but often it's only one. And that's the variable you want to know. Given all this information, do I need my umbrella? Given all this information, where's the ghost? Give me a distribution over that thing I don't know, given what I do. And so what you want to compute here is you want to compute the probability of the query given all that evidence that you have. Now, there's another class of variables. These are variables that you don't know, so they're not evidence. You also don't care about, so they're not query variables. So, for example, in that Ghostbusters case, the sensor value at a position you hadn't sensed. You don't want it as part of your answer, but you don't know it either. Those are going to be hidden variables. In a medical diagnosis thing, that might be sort of intermediate variables that sort of describe the functioning of various biological systems. It's going to be different in every in every application. But you can take your variables, divide them into evidence, which is things you know, query, things you don't, hidden, things that you don't know and also don't care about. Oops. Okay, so how are we going to compute this? There's going to be a 3-step process, inference by enumeration. You have this giant exponentially large table. Step 1, select the entries consistent with the evidence. You've already done this in a small case. So you cross out almost all of the entries. All that matters of this giant table are the ones that match your evidence. So if you know it's raining and it's hot, you cross off everything where it's not raining and hot. Okay? If you know that square 7 has a green reading, you cross off everything else. So you select the consistent entries. Then you sum out H. You take all those variables that you don't want and you get rid of those dimensions of this multidimensional array. How does that work? You get rid of them one by one, and for each one, you sum together all of the rows that now appear to be the same because they only varied on that axis. Okay, we'll talk more about this metaphor of squeezing these distributions going forward. But you sum that out. That means that what you're computing is first when you select the evidence, you get the probability of Q and all the values of H and the specific values of E. You then sum over all the values of H, and everything that collapses together goes into a table together. And then at the last step, you normalize. That's it. Take your whole distribution, select what's consistent with your evidence, collapse out variables you don't care about. You will be left with only one dimension left, which is your query, and you normalize. That's it. Any quantity you want. Now, what makes this hard is often you don't actually have the joint distribution to begin with. Once you get it, getting down to your query is easy, modulo the exponential size of everything. Okay. All right, so let's do some inference by enumeration. Okay? And when we do this, think about this as we're computing distribution over W. That's a distribution over weather. Maybe this is an umbrella bringing bot or something like that. And it wants to know what the weather is today. So given no evidence, P of W, this is a query. It also happens to be a marginal distribution because there's no evidence. Okay, so what I can do, in this case, there's nothing to kick out. There's no evidence. The whole table is consistent with my evidence, but I need to sum out, that means collapse S and T, because they're not observed, and they're not part of the query. So a bunch of things are going to collapse together. So I'm going to compute, well, W is either going to be sun or rain. And for sun, what are all of the rows that are going to collapse together? Well, it's every row that says sun. So it's this 0.3 and this 0.1, that's 0.4, 0.5, 0.65. Did I do that right? Okay, and then rain, what's that going to be? 0.5, 0.5, 0.2, 0.35? Did anybody actually check my work? Because if you think I kept making an arithmetic mistake up here, you are wrong. Okay, all right, so we have a distribution over W, which says, okay, given no evidence, I believe, given this, assuming the joint distribution is the ground truth probabilities, right, there's this question, where did we get these probabilities from? Okay, don't worry about that. That's part 3 of the course. For now, do we talk about the probability fairy and expectamax that comes in and tells you what all the probabilities are? The probability fairy gave you this, right? This is just truth. Later on in the course, we're going to have to figure out, where did that 0.65 come from? How did I know that that row was 0.3? All right, so P of W. Now let's say we have some evidence. We have evidence that it is winter. So we're going to cross out everything inconsistent with our evidence. Gone, some are gone, gone, get out of my table, you're inconsistent. Okay, so I'm left with a smaller table that's consistent with my evidence. This is the sub-table for the evidence winter. Now I still only care about P of W, so I still need to collapse out T. Okay, that hot-cold distinction. So now I'm going to get another distribution over W, sun and rain. All right, so what's sun? Well, first I have to just collapse stuff. So sun occurs here and here, right? So that's 0.25, right? And then rain occurs here and here. That's 0.25. Is that a probability distribution? Has it been normalized? It still requires normalization. So we're going to normalize, and what do we get? We divide it by its sum of entries, and so we're going to get 0.5, 0.5. Okay. Is this plausible? I thought it was 65% chance of sunny, but somebody said, hey, it's winter. My beliefs update. I'm a good rational agent. Okay. Probability of W given winter and it's hot. So, all right, we need to kick stuff out that's not consistent. Okay, consistent, consistent, inconsistent, inconsistent. Those have to do with cold. So I'm left with this even smaller distribution because I have more evidence, and I don't have to marginalize out anything. I don't have to sum anything out. There are no hidden variables, so I'm left with W. I'm left with sun, rain, and for sun I get 0.1, and for rain I get 0.05. That's definitely not normalized. So then what do I get when I normalize it? Blah. Okay, 2/3, 1/3. Nope. Yes. Okay. And so now suddenly the probability of sun goes up. So it was high, and then I found it was winter, and it went low, and then I found out, but it's actually hot, so it went back up. Now the exact values of how much it goes up or down, or whether it goes up or down at all, have to do with the specific numbers in this table. But the computations that lead to them, you can see the structural form they take. And if this table has numbers that sort of correspond to reality, then we hope that these computations will give rise to derived quantities, which are also useful. Any questions? Yes?
Do you relate the algorithm and the hidden variables to this specific example?
Yes.
What are those?
Yes. So in the first one, P of W, when I selected what was consistent with my evidence, I selected the whole table because there was no evidence. The hidden variables, the query variable was so Q, the query variable in all cases was W. So in the first one, the hidden variables are T and S. So on the axes of T and S, I needed to remove that distinction, which collapsed together a bunch of entries that needed to be summed. Once I saw that there was winter, W remained the query variable, but now the season variable S becomes evidence, but T remains a hidden variable that needs to be collapsed. And then in the end, there were no hidden variables. There were just T and S as evidence. And so as I observed evidence, things that were hidden, and I just had to sort of sum out over them, become evidence. They become known. And there's less summing I have to do, and more conditioning I have to, more selecting I have to do. Okay? So this is what you actually do with a joint distribution. Nobody's going to walk up to you and say, hey, what's the probability of winter and hot and sun? And you're going to say 0.1. That's not actually useful. What's useful are these derived conditional probabilities that tell you about variables given evidence. Okay? All right. Some obvious problems with this algorithm. You are doing exponentially large number of summations. That's bad. To store this table in the first place was exponentially large. That's actually bad. And there's a third, slightly more subtle thing, which is to learn the probabilities, you need an exponential amount of evidence because each entry has to get learned, and you're not going to learn much about it if you don't see it to a first approximation. So somehow this whole giant table of everything is not going to work. And so what we need to do is we need to build this big table out of little pieces that we can actually estimate and compute and store and then compute with efficiently. And so what we're going to talk about now is how up till this point we've talked about the tools for taking a big table and shrinking it. Now we need tools that let you turn one thing into another or let you merge things. So we're going to quickly go through those tools, and then we'll come back next lecture and we'll talk about taking it all the way the other way to very, very small pieces and then building up large distributions. So the tools you don't have, though it's possible you've seen them before in other classes, have to do with how you produce joint distributions, because we can't use inference by enumeration until we have a joint distribution. Sometimes you have conditional distributions, but you want the joint distribution. The canonical case is the product rule. This says, all right, I would like the joint distribution over x and y, but I don't have it. I have a marginal distribution over just y itself, and I have a distribution over how x behaves conditioned on y. Well, if you write out the distributions here, and you use the definition of conditional probability, you see that if you multiply p of y with p of x given y, well, p of x given y is just p of x and y over p of y. I can cross those out. And so it makes sense that the thing on the right is in fact the thing on the left, because this is basically the hidden denominator down there. Okay. When I look at this p of x given y, I actually think p of x and like a p of y kind of hanging there as a denominator that can cancel out with a p of y that's sitting there to the left, if that's helpful. So that's the product rule. How does that work? Well, let's say somebody comes up to you and says, well, I have this distribution. I know it's sunny 80% of the time. And you say, all right, well, how likely is it that it's wet and sunny? And you say, I don't know that. I don't have the joint distribution. But I do know how likely it is to be dry, given sun, and also how likely it is to be dry given wet. So I might have p of d, this other variable, given w. Okay, so right here is a distribution over d given that w is sun. It sums to 1. Uh-oh, it looks like it's been stapled to another distribution over d that also sums to 1. The bottom two rows are the distribution over d, wet or dry, given rain. The top two rows are the distribution over d, wet or dry, given sun. That is actually two distributions which have been stapled together. This is a convenient data structure. It is not a distribution. It is a family of distributions stapled together. When I sum it up, I don't get 1. Each distribution will be 1, so I'll get the number of distributions. So I'll get domain of w if I add all these things together. But this lets me do the product rule. So what I could do is I could say, all right, let's do an entry. How likely is it that it's wet and sun? Well, first it would have to be sunny. That's 80%. And then, given that it was sunny, the probability of wet is 0.1, so I get 0.8 times 0.1 is 0.08. Okay, and then I could fill in the rest. Okay, hopefully they're all there. So this is a case of going from, in this case, a marginal over W and a conditional P of D given W to the joint. Any questions about that? In general, there is the chain rule, which you may have also seen. The chain rule says that if you ever want a joint distribution over any number of variables, you can build it as follows. You can take simply the marginal distribution over the first variable, P of x1, and then you can multiply x2 given x1 to get x1 comma x2. And then you can multiply in x3 given x1 and x2, and you can keep doing this until you have all of them. It's each variable conditioned on everything before it in the variable ordering. And you say, well, that looks like a lot of symbols, and I don't believe you. So let's write the thing out. Why is this true? Well, what's P of x1? Okay, if you only want P of x1 and you have P of x1, great. Okay, but let's say you want P of x1 and P of x2. Well, I can multiply that by P of x2 given x1, which I know is the same as P of x1 times P of x2 and x1 divided by P of x1, because that's the definition of a conditional probability, and look, they cancel. What if I multiply P of x3 given x2 and x1? Well, down here, the definition of that conditional probability is P of x3 comma x1 comma x2 divided by P of x1 comma x2. I reordered them. And again, they cross out. And so each conditional probability is basically the thing you had before, crosses off the numerator and the denominator, and now you have just the joint probability. So that's all you need in order to get a joint probability, is this correct sequence of conditional probabilities. The first variable, second given the first, third given the second and the first, fourth given the third and the second and the first, and that's the chain rule. Okay, and you can see that just symbolically that has to be true, because the most recent conditional probability that you airdrop in contains the joint divided by what you have so far. All right, and so you say, okay, well, that's fine, but like, what if somebody had P of x1 and they had P of x2 but not conditioned on x1, and then they have like P of x3 but only conditioned on x1? What happens if I multiply them together? Like in general, like, right? Like you just get some number, right? There are conditions under which you can know that something less than the chain rule suffices, and we'll get into that in upcoming lectures. Okay, but for now, if you want the joint distribution, your recipe is the product rule, which is how you turn a joint into a conditional, and the chain rule, which is how you let those things telescope up to a large number of variables. Okay, one more thing, which is in fact not something new. This is, I think, a funny thing. This is Bayes' rule. It's a famous rule of probabilistic inference, but in fact, like, it's just a consequence of what you already know, even though it has a name. There are two ways to factor a distribution over two variables. So if I have P of x comma y, that's a joint distribution over x and y. I can write that as P of x given y times P of y. That's just the product rule. Okay? Or I can write that as P of y given x times P of x. That's also just the product rule. Okay? Does everybody believe that? All right. But I can send this one to this, can divide both sides by both, send them to the denominator on the other side. And what I get now is P of xy. Right, I can take this one and send it down there. P of xy is just P of x given y is P of y given x times P of x. That gives you the joint value back. Divided by P of y. That gives you the other conditional. So I like to think about this as I have the conditional y given x. I stick on P of x, it inflates to a joint distribution. And then I pull out P of y, and it deflates back to a conditional distribution of y of here x given y. Okay? Okay, that's Thomas Bayes, and that's his rule. But it's really just the definition of conditional probability written two ways, or the product rule. That's it. So what does Bayes' rule actually do? Why is this helpful? I had a conditional probability of, I wanted x given y, and so what did I do? I started with y given x, which looks basically the same, and I did a bunch of math. Why is that even helpful? The reason that's helpful is Often you have y given x and you don't have x given y, and you want to turn one into the other. Bayes' rule is a device by which you can flip the conditional around. You can build a conditional out of the reverse conditional and the appropriate marginals. And the reason that's useful is sometimes you just know one but not the other. But more generally, usually one is easy to model and the other is hard, or at least one is easier and the other is harder. So for things like speech recognition, it is much easier to model the dependency of sounds between sounds and language in one direction than the other. And of course, the direction that's easy to model is the opposite of what you want to compute. And this happens very often, is that the easy thing to model is causal, going from the cause to the effects you observe. That's the easy way to write a model. But the thing you actually want to do with the model is start with the things you observe and infer backward up to the underlying cause. And so you're always flipping things around. Probabilistic inference is almost always about taking effects and then propagating them sort of upward in the model to the underlying cause that you care about. Okay, so that's one of the more important AI equations. Like, that's really founding most probabilistic inference at some level. And so I'm not going to run through the example now, but it's in the slides for you to look at. But an example is, for example, building a diagnostic probability from a causal probability. So in generic, this is, cause. You want cause given effect, but you have effect given cause. You might know marginal probabilities of cause and effect. So for example, here's a case of a simple caricature where the cause here. The cause here is meningitis, okay, and you'd like to know whether you have meningitis. That's the random variable m. The effect is you have a stiff neck. That's the variable s. And so you'd really like to know, what is the probability of meningitis given stiff neck? If you happen to have that written in a medical textbook, you're done. You don't need to compute. But if you have a bunch of fragments of probability, you might need to do some computation. So if somebody tells you, all right, well, yeah, I don't know what m given s is. So I can't tell you how likely you are to have meningitis. But here's some things I know. I know in the population the probability of meningitis is 0.0001. Okay? That's a reasonable fact you could know. I also know from studies of people who have meningitis, I know how often stiff neck presents, maybe 80% of the time. That's a reasonable thing to know. And I also know how often sort of stiff neck is prevalent in the kind of general non-meningitis population. From this, we can then take those equations that we had before, we can churn them, multiply things, and so on, and we can end up computing the posterior probability of meningitis, which will be some small number, but it will be bigger than 0.0001. Your belief that you have meningitis given the absence of symptoms is probably not. It's like that meteor. No, that doesn't usually happen. But suddenly there's that stiff neck. You update, and you get a bigger number, but still small. So that's an example of using Bayes' rule to go from causal probabilities that you have to diagnostic probabilities you want. Slightly but not entirely off topic, if you have a stiff neck, you might want to get checked out even though the probability of meningitis is small still. Why is that? Is that because deep down you know the probability is high and that all of this Bayes' rule stuff is wrong? Is that why you get checked out? No, the probability is actually small. Why do you go get checked out? It's not about probability. What is it about? It's about utility. It's if you have it and you don't get it checked out, that's really bad. And so even though it's unlikely, when you compute your maximum utility is not the same as most likely outcome, right? And when we get to decision diagrams, we'll disentangle the difference between how likely something is, how much utility there is, and how that enters into these computations. So far, there's been no utilities. This is only talking about the likelihood of unobserved variables given variables. We'll do that next time. I'll show you one more thing, which is, let's say we have some distributions. Like we know where the ghost is, a priori, uniform distribution. And we know the sensor model. We know given each possible distance how likely the different colors are. Given that and Bayes' rule, or a generalization of it here, we can compute the posterior probability over ghost location given readings. So I'm going to do that for you in the app. And suddenly Ghostbusters goes from frustrating to fun. Okay, so here's the current belief distribution over ghost. I'm going to take a reading. Boom. Green. So there's this sweep of low probabilities. I'll take a reading up here. Yellow. Green. Going to take some more readings. See all that's jumping around? There's still uncertainty. All right. Should I sense or bust? I'm doing it. I'm going to bust right here. Right here? This is the next big video game, let me tell you. Okay, it's possible I oversold how much fun Ghostbusters is with probabilities, but you can see how useful it is to be able to compute in a precise and well-founded way this synthesis of your uncertain evidence in order to give you a belief function of your query variable. So we'll pick this up next time with talking about how to do these things efficiently over large distributions. Thank you.